In 1829, Victorian engineer Isambard Kingdom Brunel presented a design for a suspension bridge over the Avon Strait near Bristol. The bridge would be 702 feet wide and 245 feet deep at the bridgehead. Brunel's design would use wrought iron chains capable of supporting a load 5 times heavier than the load the bridge was expected to carry. Leading Victorian figures were reluctant to approve this idea, seeing it as wasteful because they didn't think it was necessary. Tell us in the comments if you think it was necessary. These engineers argued that lighter chains would suffice, but Brunel insisted on a safety margin. Construction began in 1831, but had to be stopped many times due to lack of funds. Brunel died in 1859 before the bridge was completed. His colleagues completed the bridge as a memorial in 1864. Today, 160 years later, the same bridge carries 4 million vehicles a year. Using the same chains Brunel designed in 1829, loads Brunel himself could never have imagined. In contrast, lighter alternatives that could have been built would have failed decades ago, but Brunel's chains still hold up. Under this video you will see a subscribe button. Through this small action you support the production of this and multiple similar pieces of content. During the Victorian era, many mega construction projects were built, many of which still stand and continue to serve the people of England. To learn about these bridges, skyscrapers, lighthouses, and many other mega structures, and about the masterpieces created by Victorian engineers who designed bridges capable of carrying 5 times the expected load, like the video and subscribe to the channel. The Clifton Suspension Bridge was proposed to solve a real problem. Bristol's Hotwells district lay on the western side of the Avon Gorge, while the city centre was on the eastern side. Crossing required either a 4-mile detour around the gorge or a dangerous descent to the river, followed by a ferry crossing. A bridge would eliminate both. In 1829, Bristol merchant William Vick left £1,000 in his will to finance the construction of a stone bridge across the gorge. By the time this legacy reached £8,000 in 1829, suspension bridge technology had advanced enough to make an iron bridge possible. The Bridge Committee organized a competition. 22 designs were submitted, and Brunel's design won. Brunel was 23 years old. He had assisted his father, Mark Brunel, on the Thames Tunnel project and understood the importance of building beyond minimum requirements. The Clifton design included wrought iron suspension chains with a capacity of 12,000 tons. The expected load, the weight of the bridge deck itself, plus pedestrians and light vehicles, was 2,400 tons. A 5-to-1 safety factor was unprecedented. Suspension bridges of the period used safety factors of 2-to-1 or 3-to-1. Brunel's proposal was rejected as extravagance by cost-focused committee members who argued that lighter chains would reduce construction expenses. But this is where the story truly began, and Brunel defended his design on several grounds. First, suspension bridges were a relatively new technology. The behavior of wrought iron under continuous tension was not fully understood. Secondly, winds sweeping across the open bridge deck had significant potential to create dynamic loads, far exceeding static calculations. Thirdly, no one could predict the modernity of the coming century, so durability had to be an essential feature. A bridge designed for pedestrians and horse-drawn carriages might one day carry heavier vehicles. Fourth, and most importantly, wrought iron deteriorates over time due to corrosion and fatigue. Designing for 5 times the expected load allowed room for material degradation. The committee eventually accepted Brunel's arguments, and bridge construction began in 18. Yet the challenges immediately became apparent, because the Avon Gorge at the bridge site was 245 feet deep with near-vertical limestone cliffs. The tower foundations had to be excavated with great solidity, and the ground to be excavated was rock. On the Leigh Woods side, workers dug through 30 feet of soil and broken rock before reaching solid limestone. On the Clifton side, bedrock lay closer to the surface, but groundwater seepage complicated the work. Each tower foundation required mass concrete poured into excavations 25 feet deep and 40 feet square. The concrete was prepared on site by workers using lime, sand, and aggregate transported into the gorge by rope and pulley systems. The towers themselves were designed as hollow stone piers filled with rubble and lime mortar. Each tower rose 86 feet above the edge of the gorge and extended 25 feet below ground. The masonry was built from locally quarried pennant sandstone, with joints staggered to distribute loads. Iron tie bars were embedded vertically within the masonry to provide additional tensile strength. The saddles atop each tower, the curved iron structures carrying the suspension chains, were cast in sections and bolted together on site. Each saddle weighed 6 tons and was designed to allow the chains to move slightly under load so that the stone structure would not crack. Work progressed slowly because the budget allocated for the bridge repeatedly ran out, causing construction to halt multiple times due to funding shortages. Political instability during the 1830s and 1840s made fundraising difficult. By 1843, only the towers and abutments had been completed, and the chains had not yet been manufactured. Brunel moved on to other projects. The unfinished towers stood as a monument to an incomplete vision. Local residents referred to them as Brunel's folly. Then Brunel died in September 1859, at the age of 53, exhausted by decades of relentless engineering work. His colleagues at the Institution of Civil Engineers decided to complete the Clifton Bridge as a memorial. They appointed William Henry Barlow and John Hawkshaw to oversee construction. Barlow and Hawkshaw reviewed Brunel's original design and found it fundamentally sound but expensive. They proposed using chains salvaged from Brunel's Hungerford Bridge in London, which was being dismantled to make way for a railway bridge. The Hungerford chains were lighter than Brunel had specified, but still provided a 4-to-1 safety margin, which they considered sufficient. The assembly of the chains required precise coordination. Workers first stretched temporary ropes across the gorge, then used these to position heavier wire cables. The cables supported scaffolding from which the iron chain links could be lifted and connected. Each chain consisted of multiple interconnected wrought iron bars suspended from the tower saddles. The chains carried vertical iron rods every 8 feet, which in turn supported the timber bridge deck. The entire structure was designed to flex under load. Suspension bridges derive their strength not from rigidity, but from controlled movement. The bridge deck was built from longitudinal and transverse timber beams and covered with wooden planking. The deck was 31 feet wide, sufficient for 2 lanes of traffic. Iron railings lined both sides, and decorative sphinxes were placed on the Clifton side as an aesthetic touch. The completed structure weighed approximately 1,500 tons, lighter than Brunel's estimate due to the use of a timber deck rather than iron. This increased the safety margin slightly above the calculated 3.5 to 1. The Clifton Suspension Bridge opened in December 1864, 5 years after Brunel's death. The opening ceremony attracted thousands of spectators who crossed the bridge on foot in admiration of the engineering. Tolls were immediately introduced. Pedestrians paid 1 penny, while vehicles paid more according to weight. The tolls financed ongoing maintenance and eventually cleared construction debts. The bridge quickly became an essential part of Bristol's infrastructure, carrying far more traffic than Brunel had foreseen in 1829. The bridge's survival over the next 160 years validated Brunel's cautious approach. Several factors justified generous safety margins. First, traffic increased dramatically. What began with pedestrians and horse-drawn carriages evolved into motor vehicles by the 1920s. Cars, lorries, and buses generated loads and vibrations unimaginable in 1829. Because the chains were designed for much heavier loads than early traffic demanded, they absorbed these new stresses. Second, wind loads proved more severe than calculations had predicted. Winds funneled through the Avon Gorge produced forces strong enough to close the bridge during storms. The robust chains prevented catastrophic oscillations that destroyed lighter suspension bridges elsewhere. Third, material degradation occurred as Brunel had warned. Wrought iron slowly corroded over decades, especially where water collected between chain links. Regular maintenance and replacement of worn components kept the structure safe, but only because the original design included excess capacity. The most dramatic validation occurred in 1885, when a sudden storm struck the bridge during construction work that had added temporary weight to the deck. Wind and additional load combined to produce forces approaching design limits, and the incredible happened. The chains held. The bridge flexed violently, but did not collapse. Subsequent inspections found minor damage to some connections but no fundamental structural failure. Had the bridge been built with a 2-to-1 safety margin, as some engineers had proposed, the 1885 storm would likely have caused collapse. Over time, modern engineering analyses confirmed Brunel's decision. Studies using computer modeling calculated the Clifton Bridge's actual load capacity and compared it with operating stresses. The chains can support approximately 6,000 tons under static load. Under dynamic loads caused by wind and traffic, the safety margin falls to roughly 2-to-1, still considered acceptable by modern standards but potentially insufficient, had the bridge originally been built lighter. The degradation of wrought iron over 160 years is estimated to have reduced capacity by 20 to 30%. This means that a bridge built in 1864, with only a 2-to-1 margin, would today be operating close to failure loads. Brunel's generosity preserved functionality. Remarkably few changes have been made to the bridge. The timber deck was replaced in the 1970s with a steel and concrete deck to carry modern traffic loads, while the suspension system remained Brunel's design. The chains have been inspected and maintained, but never replaced. Individual corroded links were changed during routine maintenance, but the overall structure remains original. The towers stand exactly as built. The saddles function as designed. A bridge completed in 1864 continues to carry 21st-century traffic because it was designed for loads that did not yet exist. The economic argument against overbuilding proved wrong. Critics in 1829 claimed lighter chains would save money. Over 160 years, operating the Clifton Bridge has cost less than replacing it. A modern suspension bridge built to minimum standards in 1960 would likely require replacement by 2030, a lifespan of 70 years. Clifton Bridge has served for 160 years and shows no sign of requiring complete renewal. The initial cost was higher, but the cost per year of service was lower than any alternative. Building for 5 times the expected load was not extravagance. It was economy measured across centuries. The production process of this remarkable construction project reflected the same logic that created a 5-to-1 safety margin in the suspension chains. The same logic that produced 6-foot-thick fortress walls, 4-foot-thick factory walls, and 3-foot-wide sewer tunnels. Victorian engineers consistently built structures stronger than required because they understood that such works could not easily be replaced and that future demands were unpredictable. Clifton Bridge demonstrates this philosophy in its purest form, designed for loads that would not exist for a century, built with margins that seemed absurd to contemporaries, and still functioning exactly as intended because its designer refused to optimize merely for known conditions. Brunel never walked across his completed bridge. He died 5 years before its completion, carrying the exhaustion of decades spent pushing engineering beyond conventional limits. Yet he built knowing the bridge needed to outlive his own predictions. The 5-to-1 safety factor was not insurance against calculation error. It was an acceptance that the future cannot be calculated. Today, modern vehicles crossing the Avon Gorge rely on chains specified while Queen Victoria was still young, carrying loads Brunel never imagined, and proving that engineers who design for the unknown serve their communities far better than those who optimize only for the present. The Clifton Suspension Bridge remains in daily use. 4 million vehicles cross it each year, paying tolls that fund maintenance and preserve Victorian engineering, not as a museum piece, but as functioning infrastructure. The chains flex under load exactly as Brunel intended, and the towers stand unwavering. The bridge that critics called excessively strong outlived every alternative and demonstrated that structures built for impossible loads often prove the most practical solution over time, and as a result, the bridge is still alive and standing proudly today.